Hi, I'm Minseok Jeon. Today I'm going to present our paper, Learning Graph-Based Heuristics for Pointer Analysis without Handcrafting Application-Specific Features. This work is co-worked with Myungho Lee and Hakjoo. We are from Korea University. Pointer analysis is a fundamental program analysis technique which plays a key role in various software engineering tools. For example, it is widely used in automatic program repair, bug finder, and symbolic execution tools. And the performance of these tools heavily depends on the quality of underlying pointer analysis. For example, a program repair tool cannot repair programs properly if the underlying pointer analysis is imprecise. Because the pointer analysis directly affects the performance of the software engineering tools, it is important to make the pointer analysis precise and scalable. To do so, various analysis heuristics are designed. For example, the context sensitivity heuristics make the pointer analysis cost-effective by deciding which method calls to be analyzed precisely. Without context sensitivity heuristics, the pointer analysis becomes too expensive or imprecise. This figure presents the performance of fully to object sensitive analysis, which analyzes all method calls precisely, and the context insensitive analysis, which analyzes all method calls coarsely. To compare the performance of these two analyses and to show the necessity of context sensitivity heuristics, we use the program findbox. Here, the x-axis presents the number of alarms and the y-axis presents the analysis cost. The better the performance of the analysis, the closer to the left bottom corner of the figure. As you can see, the two object sensitive analysis is precise but too expensive to be used in practice. Meanwhile, context insensitive analysis is cheap but imprecise. However, with context sensitivity heuristics, pointer analyzers can become cost-effective by assigning different contexts for each method call. For example, a heuristic scalar assigns coarse context to method calls when analyzing them with expensive context would blow up the analysis cost. As the results of scalar shows, such heuristics are essential for pointer analyzers to become precise and scalable. Then the question is, how can you design such qualified analysis heuristics? Recently, the use of graph-based heuristics has emerged as a trend in pointer analysis. Since 2016, using the graph-based heuristics has become a promising way to develop cost-effective pointer analyzers. And various graph-based heuristics have shown their effectiveness at premier conferences like Ph.D, OOPSLA, FSC, and SAS. Now I'll briefly explain how the graph-based heuristics work. The graph-based heuristics generally follow this workflow. First, they use a cheap pre-analysis to transform the given program into a certain type of graph. The types of graphs are diverse to their purpose. After the graph construction, the graph-based heuristics reason about the graph structure to produce a program-specific analysis policy for the main analysis. Generally, this policy is a classification of nodes in the graph. For example, if the policy is about assigning different contexts to each node, the main analysis will assign the different contexts to the method calls of the programs. However, there is a problem. Although graph-based heuristics are promising, manually designing such qualified heuristics is challenging. It requires high expertise in point analysis, as well as the graphs, representing the useful information. Moreover, it also requires lots of human effort. As a result, the applicability and accessibility of this promising approach are limited. Thus, our goal is to make this promising approach more accessible and applicable by automating the heuristic design process. Our technique is different from the other machine learning-based static analysis techniques in terms of designing features. In the previous data-driven static analysis, they handcrafted application-specific features to learn analysis heuristics. For example, They manually designed features to learn flow sensitivity heuristics, context sensitivity heuristics, and the other heuristics. It is obvious that such qualified features are essential for better point analysis, but handcrafting these features is a non-trivial task even for the expert. Unlike to the previous works, our technique does not require such application-specific features, and the effort as well. This fact is depicted by the title of our paper, Learning Graph-Based Heuristics for Point Analysis without handcrafting application-specific features. Instead of designing the features, we automatically generate qualified features. This is an overview of our technique, Graphic. It takes graphs of code bases and a static analyzer as input. From the input, Graphic produces a graph-based heuristic, which is represented as a sequence of sets of features. Each sequence presents nodes to be assigned with the same label. Here, the label means the context. For example, the sequence applied to OBJ presents nodes that need to be analyzed under to-object sensitivity. The generated heuristic will take an unknown graph and classify the nodes for the main analysis. Now, I will show how a produced heuristic classifies the nodes from a given graph with a simple example. Let's say a given graph consists of 7 nodes, and a given heuristic consists of a singleton set of a feature which present nodes that need to be analyzed precisely. From the given graph, the heuristic finds the nodes matching the feature. The feature retrieves nodes of which successor has at least 2 incoming edges and a predecessor with at least 2 outgoing edges. In the given graph, only the nodes N5 and N6 satisfy such property. All the other nodes are not selected as they have no successor or predecessor. Thus, in such classification, only the nodes N5 and N6 will be analyzed precisely in the main analysis, while the others are not. Obviously, the features determine the performance of the heuristics. For example, if the feature is changed not to consider the successor, it additionally chooses the nodes N3 and N4. With such classification, the main analysis will become more precise yet more expensive, as they analyze more nodes precisely. This is the performance highlight. These two figures present that Graphic successfully produces cost-effective heuristics. In more detail, we used Graphic to generate a context sensitivity heuristic from object allocation graph that the state-of-the-art heuristic scaler uses. To show the generality, we also used Graphic to generate a heap abstraction heuristic from field points to graph that the state-of-the-art heuristic Mahjong uses. For both instances and graphs, Graphic automatically generates competitive heuristics, which are both precise and scalable. Now I will explain the details. This is the syntax of our feature description language that Graphic uses to generate features. A feature is a list of abstract nodes, and the list always contains a target abstract node. Each abstract node is a pair of intervals which present a number of incoming and outgoing edges. Each feature presents a topological property of nodes in graphs. Let's assume a feature with 3 abstract nodes and graph with 5 nodes are given like this. From the graph, the feature chooses nodes which have 2 incoming edges and has a predecessor with 2 outgoing edges, which also has a predecessor with at least 2 outgoing edges. From the graph, the feature returns the singleton set N5 because only the node N5 satisfies such property. Now I will explain how to generate the sequence of sets of features from the given graphs of training programs. First, the algorithm finds the optimal labels for the nodes in the given graphs. Fortunately, there exists an efficient algorithm which iteratively runs analyzers with various classification and finds an optimal one. After the labeling task, our algorithm transforms the node with each label into a set of features. When the algorithm transforms the labeled node into features, it produces features until the generated features cover all the labeled nodes. When generating features, our algorithm uses the score function, which calculates the portion of the chosen labeled nodes over the chosen nodes. A qualified feature will have a higher score because it will choose labeled nodes but exclude the non-labeled nodes as many as possible. The goal of learning algorithm is to generate high-scored features until the generated features cover all the labeled nodes. Now I will explain how a feature is automatically generated. Our algorithm starts from the most general one, which always chooses all nodes from a given graph. Then, our algorithm enumerates possible specified features from it. A feature can be specified by cutting an interval of the abstract nodes in half or attaching a predecessor or successor. In the example, we assume the maximum number of incoming and outgoing edges of the given graphs are 194 and 280. After the enumeration, it uses the score function to choose the best scored one among them. Our algorithm repeats the enumeration until a specified feature has a better score than a hyperparameter gamma. The value of gamma plays an important role in the performance of the land heuristics. If we use too high value of gamma, the overfitting problem occurs. In this case, the land heuristic is cost effective only for the training programs. Not to face this problem, we trained heuristics with various values of gamma and chose the one performing the best for the validation program. After our algorithm produces a qualified feature, it relabels the nodes chosen from the feature to produce a different qualified feature in the next iteration. Our algorithm repeats this process until all the labeled nodes are covered. If all the labeled nodes are successfully transformed into features, the algorithm returns the sequence of sets of features as a graph-based analysis heuristic. Now, I will show the experimental result. In our experiments, we used Dupe, a state-of-the-art Java pointer analyzer. We used Graphic to produce context sensitivity and heap abstraction heuristics, which affect performance the most in Java pointer analysis. To show the effectiveness of the learned context sensitivity heuristic, we compare it with existing graph-based heuristics, Scalar, and Zipper. Compared to Scalar, Graphic shows a better precision with some loss of scalability. Compared to Zipper, Graphic consistently shows a far better scalability. For the program JEdit, Graphic performs the best. It is even more precise and scalable than Scalar, and Zipper is unable to analyze the program within the time budget 3 hours. We also compare Graphic with Data, a previous machine learning-based context sensitivity heuristic with pre-designed features. Although there are no such pre-designed features, Graphic successfully generates a competitive heuristic. In our evaluation, Graphic consistently shows a far better precision than Data. To show the generality of our technique, we also applied Graphic to generate a heap abstraction heuristic. We used field points to graph Mahjong uses. Compared to Mahjong, Graphic shows a better scalability with some loss of precision. For the program bloat, Graphic successfully analyzed it, while Mahjong failed within 3 hours. I would like to summarize this talk. We introduced a technique Graphic, which automatically generates graph-based heuristics. The two key ideas made it possible. The first one is the general feature description language, and the second one is our learning algorithm. Graphic is generally applicable to various heuristics and graphs. Thank you for listening my talk.